Hello, welcome back to the classroom. My name is Mr. Wong. Today we'll be going through a couple of questions for Module 5, Advanced Mechanics. So that's things related to projectile motion and all that. So we're just going through a set of multiple choice questions. These are the additional sample papers published by NESA, and let's go through some of them. So question 1, it says an object is projected upwards from the ground following the path as represented here. So we have a projectile motion. Which of the following describes the projectile's horizontal and vertical acceleration at point Y? Okay, so we know that for projectile motion, there is always, at least the assumption we make, there is always a constant acceleration due to gravity vertically. Okay. Now the fact that we get a shape similar to a parabola is because not only is it accelerating at a constant rate vertically, but because there is no acceleration in the horizontal component. Okay. So the thing that will match this response, let's have a look, is D. The horizontal acceleration is 0 and the vertical acceleration is 9.8. Okay, now we go to question 2. Some students were testing the hypothesis that launching a projectile at an angle of 45 will give the maximum horizontal range. Which experimental setup is best to test this hypothesis? So in these responses, we have different launch speeds and different launch angles, or some have the same launch speed, some have the same launch angle. So the question is, which would be most suitable when it comes to testing a hypothesis if 45 degrees is the most appropriate angle for maximum range? Well, firstly, this comes down to a couple of setups. One is about a term called validity. Okay, so validity is what we try and do to ensure that we're testing the aim of our investigation. The aim of our investigation is to test for angle. Okay, so angle should be the thing that we change. Otherwise, we can also call this the independent variable. So this should be the thing that is continuously changing. In that case, the speed should be our controlled variable. Right? So if we keep the speed constant, then we know for sure that has no effect on the overall range. Because if we recall, the formula for range is this. If we can make this constant, the angle in which it's launched is the only other thing that can change what the horizontal speed is. This launch speed obviously is the vector component speed. Okay. So there's that. So we're left with the option of B and we're left with the option of C. We're not picking A because we aren't changing the angle, which is not what we want. We want the angle to change. And we can't pick D because we have two changing variables. Okay. So C is actually the correct answer here. Notice how there is a larger sample size. So we're increasing each launch by 10 degrees, whereas this one is a 1 degrees increase each time. So by having a smaller sample change, we're less likely to validate our own investigation. If my sample size is very small, I don't know if I've tested the sample properly. I don't know if I have enough information to give myself a sort of confirmation of what I was trying to investigate. So that's why C is the correct answer here. All right, and now we get to question 3. So we have a ball that's launched at speed u at an angle of theta from the horizontal shown. P is the highest point, like that. Ignoring air resistance, what is the speed at point P? So at maximum height, the velocity in the y component is 0, so we only have the velocity of the u component added on. Okay, so it certainly won't be 0. It won't be u because, as you can see, this is a vector component, which means there is a vertical and horizontal component to it. So how do we work out this line here? Okay, so this is the line we want. Well, based on general trigonometry, we are looking at u cos theta, because that's the relationship. We have the hypotenuse and we have the adjacent side. So in this case, C would be our answer. Question 4. The horizontal and vertical components of the velocity of a projectile are respectively Vx and Vy. Which pair of graphs best represents the velocity of the projectile? So we have this one, this one, this one here. Okay, so which one? Oh, it's actually all the ones down here. So let's just go through each one. Okay. Components of the velocity of a projectile. Which pair best represents? So if we're looking at a normal projectile, I guess we're just assuming what the launch looks like. So projectile looks like so. The horizontal velocity is always going to remain constant. So A, B are the only ones that we can look into. So it's either A or B. Y in this component, the reason why it goes in this kind of parabola shape is because it's slowing down as it goes up, stops here, and then it speeds back down this way. So this is the best way of describing it. As the projectile is moving up, it's getting slower, so it's going towards 0, and then it speeds up but in the opposite direction. So that's what we see here. So the answer for 4 is B. So question 5, we have a torque is applied on nut using a wrench. Which change will increase the magnitude of the applied torque? So torque is the radius from where the pivot point is times the force you apply to it. So increasing the angle between the applied force and the wrench. So we also have a description of this. So if we have the force applied to the radius, the maximum amount of torque produced is when these two components are at 90 degrees to each other. So keep that in mind. Decreasing the angle, increasing the distance between the nut and the point of application of the force, decreasing the distance between the nut and the point of application of the force. Okay, so we want to increase that distance. By increasing that distance, this goes up, and by natural expectations, torque also increases. Okay, question 6. A student wants to evaluate the relationship between centripetal force and speed. The student connects a tennis ball to a rope and swings it in a circle horizontally. So if you kind of imagine you're looking on a side view, it's kind of rotating like so. Which of the following needs to be kept constant to ensure a valid experiment? So we want to evaluate this. If we look at the formula, Fc equals to mv squared over r. So using our formula for centripetal force, the answer would be D here. As you can see from the formula, mass and radius, which is in this case the length of the rope, will need to be kept constant in order for us to identify whether or not there is a relationship between centripetal force and speed. So that's why M and R need to be kept constant. That's why D would be your answer for this particular response and not the other three. Is question 7. A 15-gram metal ball bearing on a string is swung around on a pole in a circle radius of 0.8 meters. Horizontally, the angular velocity is 4 pi rads per second. And what is the magnitude of the centripetal force required to maintain the motion of the ball. Okay, so we know that centrifugal force is B squared over R. Okay, do we have any other information that we might need? Nope. So we already have majority of the info we need. We have 15 grams. We have the radius, which is 0.8. Then we have the angular velocity. So we need to try and convert angular velocity into linear velocity. Okay. The formula for that, from just the top of my head, V equals to R omega, omega being the velocity. We have a radius of 0.8 times 4 pi. So we could just leave it as this number. So I'll do that. So we have 3.2 pi. I'll just leave it at that value, just makes life a little bit easier when we put it into the calculator. So let's substitute that in and see what we get as a value. Whoops, I should also quote that that should be a -3, not -13. Don't know where I got that number from. So we have a magnitude of around 1.89 newtons, which is B. Okay, so now we move to question 8. A satellite is orbiting a planet at a fixed altitude. Which row of the table correctly identifies the magnitude of the work done by the forces on the satellite and the reason for this being the case? Okay, so if the satellite is in a fixed orbit, so if we assume that's the planet and we have a satellite that's just moving around, remember the definition for work done is force applied in the parallel direction of motion. Now the motion is going here, the force is going into here. So technically speaking, there is zero work being done on the satellite as it orbits around the planet, and the reason being acts at 90 degrees to the direction of motion of the satellite. So there's that. There is a net force, it's going in this way, but the more correct idea is that it's 90 degrees to the actual motion. And from what we say with work done, if it's not if it's parallel, you get maximum work done. If it's perpendicular, it's considered zero work done, because you're not moving in the same direction as, you're not applying the force in the same direction of motion. Okay, next one here. We have planet has twice the mass of Earth. The acceleration due to gravity on the surface of this planet is half of that of Earth. So if the Earth has a radius of 1, what is the radius of planet X? Okay. So we know what the formula for calculating acceleration due to gravity on a planet is. Whoops, I'll change that. GMR squared. Okay. So this planet has twice the mass of Earth, so we put a 2 here to represent 2m. The acceleration due to gravity on the surface of this planet is half of that on Earth. So, is that? So, assuming that these are all constants, we just let them be equal to 1. Okay, so we can just rewrite this 2r squared. So if we move this 2 over, it is 1 over 4 equals 1r squared. Flip it around, so r squared equals to 4. So the radius is 2 times as big. Whoops, should go into that. So the radius of planet X should be twice that of Earth. Okay, question 10, it says the table shows about the solar system. What is the period of another planet if it orbits the sun at an average distance of 3.5 astronomical units? So in this one, we're actually applying Kepler's third law, r cubed over t squared. We can use the Earth to help us find the constant. Remember, this constant applies to any planet that orbits or anything that orbits around the sun. Okay, so our other planet can just be written on like this. If we know the constant from Earth or Mercury, we can then use that to help us find the period for that particular planet. I'm just going to flip this equation around first because I want to make t squared the eventual subject. This becomes TO RO that. So it'll be, oh, I don't know why I wrote E there. It should be R. So we have t squared r cubed times r cubed of the other planet. Okay, and if we square root it, that will give us t. So in terms of, if we just, I guess, better off showing you the numbers, time is 365 days divided by the radius, which is 1 cubed, times the astronomical units of 3.5 cubed. Let's see how long it takes this planet to orbit around our sun in terms of days. Okay, so in this case, according to what I got, roughly around 2,390 days if we round it off to about 3 sig figs. So the closest answer to that is B. And we have the answer there. There should be one more left. Question 11. Okay, so we have two identical masses placed at points P and Q. The escape velocity and the centripetal orbital velocity is given by these following values, or following wording. That mass, or the escape velocity and circular orbit velocity of mass at point Q is that and that. The diagram to scale, or is drawn to scale, and X denotes the center of Earth. Okay, the velocity for a body in circular orbit is given by the following formula. What is the value of the escape velocity of Q over the orbital velocity of P? Okay, so we need to know the relationship between escape velocity and orbital velocity. Escape velocity is 2 pi times orbital velocity. Okay. If you don't know how to derive the value for escape velocity, which is this one we have here, you'll need to go back to one of the videos we talked about in deriving that using potential energy and kinetic energy. Okay, so what is the value of that? So we know that both of them have the same mass. They have a different radius. So what is it? 2 times the amount? Let's see. So it looks like twice the amount. It's drawn to scale, so that's twice the amount. And then we have to go from there. Okay. So if we look at the escape velocity of Q, it's 2 gm times 2r of p. Okay, we're talking about this relative to p. So these two cancel each other out and we get a value of gm over r. If we're going to look at the orbital velocity of p, which is gm over r, okay, the radius is 1, relatively speaking, because we're using that distance there. The mass is exactly the same, so it'll be pi gm over r over, or square root, sorry, over gm over r. So we get 1 over rho from that value. So the answer would be B, sorry. I don't know what I'm saying. It must be a very long video. Yeah. So the value of the escape velocity of Q divided by the orbital velocity of P is 1, and B is the answer there. So that one was quite a tricky one. As you can see, it's a band 5 to 6 if you're aiming for it. But that's essentially all the multiple choice questions of the additional sample paper. If you found that useful in explaining how to go through each one, please hit the like and subscribe button if you haven't done so already. And I'll see you next time, where I'll try and cover some other Module 5 advanced mechanic questions. Thank you for listening.